In this video, we will build memory address register and memory for our 8-bit CPU. Welcome back to the channel, guys. So in the last video we built ALU for our 8-bit CPU. In this video we are going to build memory address register and memory for our 8-bit CPU. For those of you who are new here, this is the 6th video in the series 8-bit CPU on FPGA. So if you haven't watched the previous videos yet, please go back and watch those videos first and then continue watching this video. If you haven't subscribed to the channel yet, please subscribe and help me reach my 1000 subscriber goal by the end of this year. So without wasting any time, let's get started. So first we are going to build memory address register. Memory address register will be same as normal register, just it will be 4 bits wide and it will only have output which will be constantly outputting address value for our memory. So I'm going to copy our register file as is. So and we will name this memory address register. So mar.vhd, and we will change the entity name. Okay, and its input will be 4 bits, so 3 down to 0. We need only one output which will be connected to memory, and that output will be there will not be any enable pin to enable that output. So once you load the memory address register with some address, that address will always be available on output line. So I'm just putting output ALU port. Let's change that name to output. So as you know from the general purpose register, output ALU gives constant output to our ALU. So here it does the same for memory. Now stored value, again this will be 4 bits wide, and I think we don't need output enable, so I'm just removing that input. And since we don't have output enable, let's remove this line. And let's change this to output. So basically this is our memory address register, not very different from our general purpose register. And I'm not going to write a test bench for memory address register because this is very simple and exact. I mean, it's very similar to our normal register. So let's move on to our memory, and then we will write a test bench, a combined test bench for both. So speaking of memory, we have 4-bit address space, so our memory is able to store 16 bytes of data. So as you can see in the block diagram, our memory will have a clock input, then it will have load input which will be high when we want to load a value in memory. Then it will have output enable. So when output enable will be high, memory will output the contents of address to the to the bus. So it will have data in bus, so that will be 8-bit wide. Then we will have address input, which will come from our memory address register's output. That will be 4-bit wide. And lastly, we will have data output, which will be 8-bit signal, and it will output the data to our bus. So this is the memory. So let's start to write this in our memory.vhd file. So I will make entity with name mem is let's store this as mem.vhd. So let's define all the inputs and outputs. First will be clock. This will be input and standard logic vector. Not logic vector, logic. It will be standard logic. Then we will have load signal. This will be same standard logic. Then we will have output enable. This will be also standard logic. Then we will have data in. This will be input of standard logic vector, and this width will be 8 bits, so 7 down to 0. Then we will have address input. I will name it ADDR in. This will be standard logic vector of 4 bits. So as I said, this will come from our memory address register we just made. So its output of 4-bit will be connected to input. And lastly, we will have data out. This will be output of standard logic vector, and the width will be 8 bits, so 7 down to 0. So this is our entity. Let's start to write our architecture. So we in this memory we will store data in an array of type standard logic vector, which will be of width 8 bits, so 7 down to 0. So for that we need to make a custom data type. So let's make that data type. So I will say type mem type. Let's call this is, this will be array and the array length will be sorry about that. Array's length will be 16, so 0 to 15 of standard logic vector 7 down to 0. So this is just a data type. We will need to define an object of that data type soon. So let's write our process. So in this process, on rising edge of clock, we will check if rising edge, then we will check if load is high. If load signal is high, then it means that we have to store whatever value on input line into the memory, and the address will be specified by memory address register. So if load is high, then we will store the data input into our memory object. So first we need to make memory object. So I will here define signal memory object of type memory, memory type. Oh, just one spelling mistake here, not meme type, it's mem type. So and we will store whatever value on data input, so that would be data in, to our memory object, and the address where we want to store will be defined by address in line. So we will convert that 4-bit value to integer. Since our 4-bit value is unsigned, so we have to specify that, and then our input line, so addr in. So this will store the input into our memory. So now we will write if output enable is equal to 1, then here we have to output the data to data out, and again the which address to output will be specified by our address in line. So again I will just copy this line and paste here. So this is our memory. Let's specify the default value for our data type. So we will assign this to high, that is Z. So let's add these two files to our ModelSim project, and let's check if we have any errors. So let's add our files. Memory address register and memory.vhd. Let's compile them. Okay, so our memory address register is compiled successfully. It was going to be because we just copied our general purpose register there. Okay, we have some errors in line number 19. I think we cannot assign a default value like that. That's why it's giving error. Okay, for using two integer function, we need one more. We need to use IEEE library numeric standard. So let's just add that. Now it should compile successfully. Yes, it's compiling. So that's it for the memory and memory address register. Let's make a test bench quickly. I'll just copy one of the test benches here. Program counter, it doesn't matter. So I will save this as MAR test bench. Let's rename the entity. We will need both memory address register and memory component here, so let's just copy. Let's just copy the port of memory as well. We will need clock signal. We don't need reset signal. Okay, we will need two load signals, one for memory and one for memory address register. So let's just define the signals here. Signal load for MAR, load for memory. Then we will need 4-bit input signal. 4-bit signal for MAR input. So let's just define standard logic vector 3 down to 0, and 4-bit signal for output as well. So MAR output. Okay. Now we will rename this enable to memory enable and load to memory load, so we are able to differentiate between the memory and memory address register signals. So memory input signal will be 8-bit wide, memory output will be 8-bit wide. Let's just append memory to this so that we are able to distinguish between the two. Yeah, so these are all the signals that we need. So let's just make an instance of memory address register MAR1. So clock will be clock signal. Okay, we need reset. Let's just make a reset signal here. Connected to reset signal. Then load. So load of memory address register will be connected to load MAR signal. Then we need input. So input will be connected to MAR input, and output will be connected to MAR out. So these are memory address register connections. Now we will make an instance of memory with the name memory1. So memory's clock will be connected to clock signal. Our memory does not have any reset signal, so load output enable. Data in, address in. And data out. So load will be connected to memory underscore load signal. Output enable to memory underscore enable signal. Data in will be connected to memory input signal. Address in will be connected to output of memory address register. So MAR out. And data out will be connected to memory out in memory output signal. So this is the instance of our memory. Let's delete this program counter instance. I will leave the clock signal as is because we need that. Now let's keep reset as is. Let's not touch it for now. We will put some value into memory address register. So MAR input will be say 0001. We will wait for one clock and we will make memory address register load signal. So load MAR. I should really name these signals consistently so that it's easier to remember. Then after one cycle the address should be loaded into our memory address register. Then we can put whatever we want in that memory location. So memory input will be reflected on the output line of memory address register, which is connected to our memory. So now we can put some value into our memory. So memory input signal, let's give this some 8-bit value. So I have set FF for now, all ones. and here we will need to make the memory load signal high so that our input will be loaded into memory. Let's wait for one clock cycle and then make this signal low, and we will output the same value. So memory address register will not change, just memory enable signal, we will set it to high, and our memory should output whatever the contents of that memory location to output line. So let's just compile this test bench and see if we have any errors and if it works as expected. So add to project, existing file. Okay, we have 4 errors. Let's see. Okay. 49. Oh, okay, not 8 down to 0, all should be 7 down to 0. I guess this should solve our errors. Yes, it compiled successfully. Let's add a simulation configuration. Choose our test bench. Okay, I should have named it something better. Let's add all of these signals to a new wave. And just run for 1 microsecond and see if we get anything out of this. So let us zoom in here. Okay, that's too much. As you can see, our memory input line has a value of 1, and then we make load memory address register to high. So as soon as we load the value, our it is reflected on memory output register, MAR out. So an MAR out is connected to our memory input signal, I mean memory's address in, and we have put FF on memory input signal, and when we make load memory high, yeah, so memory load signal, when we make it high, that this FF value will be stored in our memory, and when we enable memory output, then on the next clock next rising edge, our output, whatever stored in memory, will be outputted to the output line. So that's it for our memory and memory address register. So if you like this video, please give it a thumbs up and let me know your thoughts in the comments. If you think I have done something wrong, then let me know in the comments as well. If you have any suggestions, please comment down so that we can improve our videos. Again, if you have not subscribed to the channel yet, please subscribe to this channel to help me reach my goal of 1000 subscribers by the end of this year. Thank you for watching this video and see you in the next video.